Hello, welcome to this video. Finally, we have arrived at the full-blown version of the Lagrange multiplier method. So, a short recap. What do we have to do? Well, we want to find the lowest possible values for fs1 and fs2, and we do that by minimizing this sum of squares, also called j, but j is equal to 0.02 times fs1 squared plus 0.04 times fs2 squared. So we have to minimize that. And at the same time, we have to satisfy this equilibrium equation. 0.02 times fs1 plus 0.02, oh, that is of course 0.04. 0.04 times fs2 equals 3. So this one has to be satisfied. This one should be as low as possible. Okay, well, the trick here is that we start by taking the minimization criterion. So we have j equals 0.02 times fs1 squared plus 0.04 times fs2 squared. And now we are going to add something to j. So I will not give you the mathematical proof that you can do this, but well, so this is one thing that you have to learn by heart. But I think it is the only thing in this course that you really have to learn by heart. Now, what we have to do is we have to add the constraint equation. And what is the constraint equation? Well, that is this one. But before you can add it, you have to rewrite the constraint equation such that it ends at 0. So we have to write this as 0.02 times fs1 plus 0.04 times fs2. And now there's on the right hand side a 3, and we don't want to have that. That there should be a 0. And you can do that by putting it on the other side with a minus sign. So minus 3 equals 0. So it has to equal 0. Well, if it is in that form, then you can add it to j. So that is what I'm doing now. And there's one more thing. You also have to multiply by a constant. This whole constraint equation has to be multiplied by a constant, and most of the times lambda is used. So again, I'm not going to tell you why this is exactly, but I think you can remember that this is what you have to do. And the rest of the story is then well, equal to what we have learned before. Because what we have now is an unconstrained problem. We started with a constraint problem. This was the constraint. So we have a minimization with a constraint. And now we end up with only a minimization. The constraint has been incorporated somehow. And now we only have a unconstrained minimization. And we know what to do with an unconstrained minimization. We have to take the derivative and equate it to 0. Okay, now we have here this fs1 variable, we have fs2 as a variable, and we have lambda as a variable. So this is a three-dimensional problem. Well, that is the reason that we now are going to write down 3 derivatives. So we have dou j dou fs1, and that should be equal to 0. And we have dou j dou fs2, that should also be equal to 0. And we have dou j dou lambda. And that must also be 0. So let's start with the first one, dou j dou fs1. Okay, if you take the derivative with respect to fs1, then fs2 is a constant. And lambda is also a constant. Yeah, those were the rules for partial differentiation. Okay, let's differentiate this one. So that is 0.02 times 2 times fs1. Okay, what happens with this part? Well, that is a constant, as I just said. So that if you differentiate it, it will become 0. Then we have, here we have 0.02 times lambda times fs1. And we have 0.04 times lambda times fs2. And we have minus 3 lambda. That is if you get rid of the brackets. Okay, now here we have a term that contains fs1. Here we have a term that contains both lambda and fs2. But of course they are constants. So if you differentiate them, they will be 0. And if you differentiate this constant, well, if you differentiate with respect to fs1, then this is a constant. And if you differentiate a constant, it will become 0. So it vanishes. Okay, so we are left with this term differentiated with respect to fs1, and that gives 0.02 times lambda. And this has to be 0. So here is our first equation that will tell us where the optimum is. Okay. Now I will give you the answers for the other two, and then in exercise 10 we will derive them. So the answer for dou j dou fs2, that is 0.08 times fs2 plus 0.04 times lambda, and that has to be 0. And we have dou j dou lambda, of course. And that's just the equilibrium equation. So that is 0.02 times fs1 plus 0.04 times fs2 minus 3 equals 0. So I think it would be nice if you try to derive this equation and this equation from this j function and then watch the video about exercise 10 so you can check whether you did it the right way.